In this last video of this week's lecture, we're going to look at some other image recognition tasks such as object detection and semantic segmentation. Primarily, we will look at how we can adapt the image classification architectures that we saw in the previous lecture for these other recognition tasks. So let's dive right in.
Detection and segmentation. In the last lecture, we discussed several important architectures for image classification. We saw that these deep convolutional architectures take an image such as this as input to the network, and we then pass them through a series of convolutional and pooling layers. And in the end, we have a bunch of fully connected layers. And finally, the last fully connected layers has the number of units as the number of classes that we have in the data set. So for this, we get the category label that describes the content in this entire image as a whole. So this is the most basic task in computer vision. And as I mentioned in the previous videos, these classification architectures are still fundamental building blocks for complex tasks that need more spatial reasoning. So now let's discuss how we can perform complex recognition tasks such as semantic segmentation and object detection. We will also look at how these more complex tasks such as instance segmentation and panoptic segmentation are performed. And we want to do all of these using convolutional neural networks. So these tasks are very highly researched today because they are extensively used for a variety of applications that range from autonomous driving to medical image analysis to remote sensing. So the interesting thing here is that as we go through these network architectures for each of these tasks, you will see that they've become more and more complex, but they sort of build upon each other. So for example, instance segmentation architectures build upon semantic segmentation and object detection architectures. And panoptic segmentation architectures further build upon instance segmentation and semantic segmentation architectures, and so on. All right, so let's first discuss semantic segmentation. So semantic segmentation is a task in which we want to input an image to a network, and we want to obtain an output classification for each pixel in this input image. So here the colors in the output denote what semantic category does the pixel belong to. For example, pixels belonging to cars are denoted in blue, pixels belonging to the road are denoted in purple, trees are denoted in green, and so on and so forth. So semantic segmentation does not differentiate between different instances. This means that, for example, if there are multiple cars in the image, as you can see here, then pixels belonging to all of these cars are classified as the same category, and it cannot distinguish between pixels from one car to another. And semantic segmentation considers the entire scene context. And this means that it considers different object classes that are present in the scene, their locations in the image space, the shape of the different objects, and so on. Therefore, this is a classic dense prediction problem. Now, what works reasonably is using fully convolutional neural networks. So rather than extracting individual patches from the image and classifying these patches independently, we can use the entire image and pass it through a stack of convolutional neural network layers and no fully connected layers anywhere. So if you assume that your filter is, for example, has 3 by 3 with padding 1, then the convolutional layer will preserve the spatial size of the input throughout the network. And when we pass this image through these stacks of convolutional layers, then the first convolutional layer can just output a tensor, let's say, of volume C times H times W, where then C denotes the number of semantic classes that you have in this data set. So if you pass this tensor then to a softmax function, you get a probability for each class C for each pixel in this image. And you can then also train this with regular backpropagation. But the problem with this is that since we are maintaining the same spatial resolution throughout this entire network, then this will be really expensive in terms of the computation. So let's see this with an example. Imagine that you have an image of size 1024 times 2048. And in some convolutions, you can even have as many filters as 128 or 256. Then computing convolutions over a sequence of such layers is going to be extremely expensive as well as memory intensive. So this type of convolutional architecture with the same spatial dimensions throughout the network is almost never used in real world online applications. So instead, what you tend to do is something like what you see in this architecture in this slide. So we have these downsampling stages in this network, and in the beginning, and then you have these upsampling stages in the end. So this downsampling path in the beginning is very similar to the architecture of classification networks that we learned about, where we have a few convolutional layers, then maybe convolutions with stride for downsampling, and so on. But we don't use fully connected layers anywhere in this encoder part of the network. So then in the upsampling part of the network, we again increase the spatial dimensions or spatial resolution of these downsampled feature maps. We then use transpose convolutional layers to do this. So we again have alternating transpose convolution and convolutional layers. That's why you see these alternating colors here. And finally, we get the output in the end in the same resolution here as the input image. So this is much more computationally efficient because now you can make the network very deep and you can have a small spatial resolution for most part of this network. And one thing here that I want to mention is that using transpose convolutions for upsampling might lead to these gridding artifacts. And it sort of looks like this pixelated effect, and it does not give you smooth boundaries along objects that we would like. So one way to address this is by just using bilinear upsampling and convolutional layers. And this works better in some applications. What we saw right now is probably the bare minimum you need to do in semantic segmentation. And the result that you will get is probably going to be quite decent. However, state-of-the-art networks are far more complex. Basically, they do the same downsampling and upsampling that you see here in this slide, but then you have various specialized modules for learning multi-scale features using dilated convolutions. Also, you have modules for capturing long-range context in the signals, and you also have modules to get smooth object boundaries, and so on. All right, next, let's discuss another fundamental recognition problem, which is object detection. Object detection is basically both classification as well as a localization problem. And here you not only want to classify objects in the image, but you also want to know where the object is exactly located in this image. And we denote that using these bounding boxes around these objects. So in the image that you see here on the right, you can see the output of the object detection network where these bounding boxes have been drawn over these various objects that are detected in the scene. And the output of the network is actually in terms of the coordinates of these boxes and not really like the colored pixels around these objects as you see here in this image. With these output coordinates that we get from the network, we just draw these boxes around the objects for visualization. What you can also see here are these colored boxes. So these colors basically denote which object is being classified by the network here. For example, here we can see that blue boxes denote cars, pink boxes denote persons, and so on and so forth. So this is because the network not only tells you where the coordinates of these bounding boxes are in the image, but it also tells you what object category is inside these coordinates. Basically, it classifies the objects that is enclosed in these bounding boxes. Now recall that the object detection is composed of two subtasks, bounding box regression and object classification. So this is similar to what we had in the classification networks, where you first feed this image into a convolutional neural network, and then you have a set of fully connected layers in the end, which then gives us the classification score. But the additional thing now is that we also have another fully connected layer in addition to just the classification score. Here in this additional layer that you have, it gives you 4 numbers as the output, where these 4 numbers denote basically x and y coordinates and the height and width of these bounding boxes that we would like to have. Now the network performs both of these tasks together, and it gives us the classification scores as well as the coordinates and the dimensions of these bounding boxes. So when we train this network, we will use again 2 losses. We will use the softmax loss for classification scores and another loss to regress the coordinates for which we can modify using, for example, an L2 loss function. So object detection methods can be broadly categorized into two-stage detectors and single-stage detectors. Two-stage detectors first perform bounding box regression and then classification, whereas in single-stage detectors, they only use one CNN for bounding box regression and classification. All right, so first came these series of papers, one after the other. The first one was called RCNN, the second one was called Fast RCNN, and the third one was called Faster RCNN. So if you note that all of these have the letter R in them, and this is because R here in the RCNN stands for regions, because they're all region-based methods. So unfortunately, we don't have time to go over each of these architectures in detail in this lecture, but I would briefly like to give you the basic principle behind them. So in these RCNN networks, we first feed the entire image into a convolutional neural network, and then the CNNs gives us convolutional feature maps, and these convolutional feature maps represent the high resolution image features. So we then have a separate region proposal network, one that works on top of these convolutional features. And then we take crops of these region proposals from the convolutional feature maps, and we then pass them through another set of layers that then predict the object class as well as the bounding boxes. So here you can basically see the difference between these 3 subsequent methods. And I would say that the main difference is how the region proposals are extracted. So in the first RCNN method, the region proposals are extracted directly from the image itself, and there is no learning in this. And in the second fast RCNN, we feed the image to a CNN, and then we extract these features from the CNN. Therefore, this is a little bit more faster. And finally, in the last one, the region proposals are basically learned using a separate network. So another difference is that in the first RCNN network, we use SVMs to obtain bounding box offset values. And in the second one, we use fully convolutional neural networks for regression and classification. And we also use fully convolutional for regression and classification in faster RCNN. Okay, so there's also this other family of methods that you can use for object detection. And this basically does everything in a single pass as opposed to the two-stage region-based methods that we saw in the previous slide. So two most famous methods are called YOLO, which stands for you only look once, and SSD, which stands for single shot detection. Here, the main idea is that rather than doing the independent processing of these regions, we want to make all the predictions at once. So given the image, we divide the entire image into these coarse grids, as you can see in this image on the right. And now these coarse grids gives us basically the base for these bounding boxes. For example, here you have square box in the middle, and then you have two rectangular boxes. Now we want the network to predict several things for each of these grid locations and for each of these base boxes. We want them to predict the offset from the base bounding box. We want them to predict the true locations of the object from the base bounding box. And we want them to also predict the classification scores. Basically, we have this huge convolutional neural network to predict all of this at once. These methods are more faster than the region-based methods, such as faster RCNN that we saw in the previous slide, but they're also a bit less accurate than the region-based methods. So really quickly, I want to explain the concept of two very related problems. These are instance segmentation and panoptic segmentation. Now, I'm not going to go into the details of how these architectures are constructed in detail, but it's still good to know what these problems are. First is instance segmentation. In instance segmentation, you not only want to segment objects semantically, but you also want to differentiate one object from another of the same semantic class. This basically means that you want to be able to say that, for example, this pixel here represents one car and this pixel here represents a different car. So here the network not only classifies what semantic object categories each pixel belongs to, but also if it belongs to one specific instance of a semantic class or a different instance of the same semantic class. This is why in the output here you see objects segmented individually and they are shown in different colors. So you can think of this problem as a combination of semantic segmentation and object detection. One of the first architectures that was proposed for instance segmentation is called mask RCNN. And mask RCNN is basically an extension of faster RCNN that we saw in the previous slides, with now a semantic module that can perform instance segmentation as well. And they do this in a single architecture. So mask RCNN follows the detect and then segment paradigm, where we first extract bounding boxes for object detection, and then we perform binary segmentation for inside each box. And as I said before, this builds upon faster RCNN. So it also inherits the drawbacks of faster RCNN. And this is slower execution time than the single shot methods. And these masks that we get from these mask RCNN methods also have a fixed resolution. As opposed to this, we also have instance segmentation approaches for the single shot methods. And this is also called anchor-free methods. And one such approach to this is the solo V2 approach. Okay, finally is this task of panoptic segmentation that you see here on the right. And panoptic segmentation is a combination of now instance segmentation and regular semantic segmentation. So panoptic segmentation basically introduces this concept of things and stuff. The categories of things contain objects such as people, cars, cyclists, and so on. And these are basically the objects that we want to do instance segmentation on. And the categories such as buildings, roads, sidewalks, which are basically amorphous regions, are the categories that we want to do normal semantic segmentation on. So basically here, what we want to do is a combination of instance segmentation for thing classes and standard semantic segmentation for stuff classes. And we want to do this simultaneously using a single convolutional neural network architecture. So if you think about this, This is far more complex problem. Now we are trying to take instance segmentation, which is an already complex task, and we are trying to combine it with semantic segmentation to yield this coherent scene perception of the environment. Okay, so panoptic segmentation methods can again be categorized into two. One is top-down methods and the other is bottom-up methods. So top-down methods tackle this problem in parallel, which means that we have a semantic stream and an instance segmentation stream. And the problem with this is that we have overlapping masks that are produced from the semantic head and the instance head, and then we need to resolve this with a specialized fusion module. So an example of this is the efficient PS architecture, which is shown here, and this was developed here in our lab in Freiburg. And as you can see, we have a backbone, which is basically a classification network. Here we use a modified efficient net architecture. And then we have two parallel streams, one that performs semantic prediction, another that performs instance segmentation. And finally, we get these overlapping predictions and we fuse them with a specialized fusion module. So now, as opposed to this, bottom-up methods take a sequential approach. And here, so first we perform semantic segmentation, followed by a grouping step to generate the instance mask. So an advantage of the bottom-up methods is that they have faster inference speed as opposed to top-down methods. But top-down methods here gives us much more better or superior performance than the bottom-up methods. All right, so this brings us to the end of this video, and I have two questions for you. What is the most naive approach to perform semantic segmentation with convolutional neural networks that you should not basically do? And what could be the advantage of performing panoptic segmentation instead of just doing regular semantic segmentation and instance segmentation separately? So this also brings us to the end of this week's lecture. Thank you, and I will see you in the upcoming lectures.